Let's do problem number 57 on page 196. And here is a problem. It's a simple little problem. It says how high does a rocket have to go above the Earth's surface before its weight is half what it would be on Earth? Okay, so let's do the given, find, and solve thing for this. Okay, what do you got for me? Julie Nguyen is getting some scholarships. Someone goody. Okay, quiet, please, because you're annoying future generations of physics students. So, not just me, but future generations. All right, so here's the Earth, which is round, isn't it? All right, and so it's got a certain radius, but a certain height, some distance out here. It says you want to be half your weight, right? Half your weight, because it says how high does a rocket have to go above the Earth's surface before its weight is half what it would be on Earth. So really, this is your weight. It's like your weight over 2. It's like you're dividing your weight in half. So and you want to find the height. So really, that's this right here. You want to find h. H is the height above the surface, where your weight is half of what it is when you're down here. Okay. So let's solve it. Now we know that the force of gravity is equal to big G times the mass of the Earth times the mass of the object divided by r squared. Now this is our weight at this location in space. Yes? Question?
Is there a shoe?
No. Okay. Now this is going to be equal to our weight on the surface at radius r. So that's GMM over r squared, but it's half of this, right? It's 1/2, but our weight out here, somewhere out in space, is half of what it would be on the Earth's surface. Now, if you want to know what your weight is on the Earth's surface, you could take your mass and multiply it by 9.8 newtons per kilogram. But you could also do this. You could say big G times mass of the Earth times the mass of you over the radius of the Earth squared, because that's how far you are from the center of the Earth, right? Is the radius of the Earth when you're on the surface. But when we're out here, we're going to be half of that. So I'm going to multiply it by 1/2. Does that make sense? So this is half your weight on the surface. That's what that represents. Now the nice thing about setting it up like this as an equality is that almost everything cancels out, doesn't it? Do you see that? I mean, this equals this. Now what are we going to solve for? Well, we're going to solve for r, little r. Well, we don't need to know the gravitational constant. It's on both sides of the equal sign. We don't even need the mass of the Earth. It's on both sides of the equal sign. We don't need to know your mass. But we do, but now we're stuck. So 1 over r squared is equal to 1 over 2 big R squared, the radius of the Earth squared. Okay? See what I did to go from here to here? Because look, The gravitational constant, the mass of the Earth, the mass of you, or whatever, everything, they're the same. I mean, whether you're on the surface or you're out here, some distance away, the gravitational constant didn't change. The mass of the Earth didn't change. Your mass didn't change. The only thing that changed is how far you are from the center of the Earth. That changed. So, so now we can, well, let's reciprocate both sides. That means that r squared is equal to 2 times big R squared. Now we want to know what r is. So r is equal to, we'll take the square root of both sides. And that's just going to be the square root of 2 times the radius of the Earth. So the answer is, well, it's not the total answer, but our location from the center of the Earth is the square root of 2 times r. A lot of people want to double it. You know, say, oh, well, if you want to weigh half as much, go twice as far out. No, if you went twice as far out, you would weigh 1/4 as much, because the force of gravity is a function of r squared. If you went, twice as far out, you would weigh 1/4 as much, not 1/2 as much. But if you, but it's the square root of 2 times the radius of the Earth. So this is going to be the square root of 2. Now the radius of the Earth, you have to look it up. Oops. But it's 6.38 times 10 to the 6 meters. So r, from the center of the Earth out to where my weight is half as much, is equal to the square root of 2. So here's square root of 2, which is 1.4142, times 6.38 times 10 to the 6 meters, and I get 9.02 times 10 to the 6 meters. Now this is not my answer. This is my distance from the center of the Earth, but what's it asking for in the problem? It's asking for our height above the Earth's surface. So what do I have to, if I want this, but now I know this, what do I have to do? Subtract the radius of the Earth. So h equals the radius of the Earth, or I'm sorry, it's equal to r, this total distance here, minus the radius of the Earth. So we're going to take 9.02 times 10 to the 6 meters minus 6.38 times 10 to the 6 meters. Oops, I'm off screen. And this should be our answer. So minus 6.38 times 10 to the 6, and I get 2.64, or 2.6 times 10 to the 6 meters above the surface. Oh, let's see if I did that right. That's number 57. Oh yeah, yeah. Now on this scale, I want you to think about it. If this is the scale of the Earth, I actually drew it farther out than I should have, because this is 2.6. Now this is this is about 6, a little over 6. So this is 2.5. So it's not quite half again as far. So, well, let me redraw it. If this is the Earth, and this is, this is 6.38. Well, you want to go another 2.6 out, which would be right about here. So if you want to weigh half as much as you do on the surface, you have to go this far out, relatively speaking. That's kind of interesting. Now, of course, you would never do this. You could never be, well, I mean, you could never build a tower this big where you can stand there and weigh that much. However, the acceleration of gravity, if you're like in orbit, or let's say you're just at rest, but you're immediately going to start falling. If your weight is half as much, what's the acceleration of gravity right here? It's 4.9 meters. So you're going to start falling down towards the Earth at 4.9 meters per second squared instead of 9.8 meters per second squared. So there's still gravity out here. Oh yeah, there's gravity out, billions of miles. Of course, if you get up really, really, really far, the gravity becomes almost negligible, almost not noticeable. But if you have a satellite way out here, that's a pretty big orbit actually, and there's still gravity. Of course, if you're in orbit, you're in free fall, and so if you're in free fall, you don't really feel as if gravity's acting on you. But if gravity wasn't acting on you, you wouldn't be going in a big circle around the Earth, because you need a force to go in a circle. Any questions? Abdu needs to go potty. That is all.